Hi, in this video we introduce logarithms and obtain a differentiation formula for the natural logarithm function based on implicit differentiation. When we write log in base 2 of 8, we mean by that the exponent y such that 2 to the y is equal to 8. In other words, a logarithm is always an exponent, and if the base is 2, then we are looking for the exponent such that 2 raised to that power will give us back the number that the logarithm is applied to. In this case, log in base 2 of 8 is equal to 3, because 3 is the exponent such that 2 to the 3 is equal to 8. If g of x is the function log in base 2 of x, then g of 8 is equal to log in base 2 of 8, which is 3. And 8, 3 lies on the graph of g. If f of x is equal to 2 to the x, then f of 3 is equal to 8, and 3, 8 lies on the graph of f. The following figure shows in red points related to the graph of f and in blue those related to the graph of g. 3, 8 is on the graph of f and 8, 3 is on the graph of g. Similarly, log in base 2 of 4 is equal to 2 because 2 is the exponent to which we raise 2 in order to get 4. Therefore, 4, 2 and 2, 4 are points that are respectively on the graphs of g and f. Following this logic, if AB is a point on the graph of G, then BA is a point on the graph of F. So we can easily obtain points on the graph of F, the function 2 to the x, simply by taking x coordinates and computing 2 to the x. Then inverting the coordinates gives us points on the graph of G to the x, the log in base 2 of x. We have done this here and joined the points by a curve. It's not too hard to convince yourself that by interchanging the coordinates of a point, geometrically this has the effect of performing a reflection across the line that bisects the first and the third quadrants. This is the line y equals x that forms an angle of 45 degrees with the x-axis. So if we know what the exponential function 2 to the x looks like, then by reflecting it across the line y equals x, we get the function log in base 2 of x. If AB is on the graph of G, then G of A is equal to B. But then BA is also going to be on the graph of F, so that means that F of B is equal to A. So therefore, if we combine the two functions, we get F of G of A is equal to F of B, because remember that G of A is B. And because F of B is A, then we get back A again, so we get F of G of A gives us back A. Similarly, if we compose G and F together, we get G of F of B is equal to G of A, again because F of B is equal to A, and then G of A is equal to B, so we get B in the end again. So the following diagram summarizes the two previous equalities. If the input is A, then G sends A onto B, and then B gets sent back onto A through the function F. So basically where we had started. This is the same as doing G of A first and then F of G of A to get back A again. So that explains why F of G of A is equal to A. And if we translate this using the fact that F is the exponential function and G a logarithm function, we get 2 to the power log in base 2 of A is equal to A. If we start at B now and apply F, we get F of B, and that's A. And if we apply G, we get G of A, but that's B. So we end up where we have started at B. So G of F of B is equal to B. And if we translate this using what our functions are like, we get log in base 2 of 2 to the B is equal to B. So we call G the inverse of F and F the inverse of G. More precisely, G of x is equal log in base 2 of x and F of x equals 2 to the x are mutually inverse functions. each function is undoing what the other does, as you can see in the previous identities, right? When we did exponent of a log, we got back the initial input, and if we did log of the exponent, we got back the initial input. So it's undoing what the other does, just like multiplication is undoing what division does. For instance, we have 2 to the power log in base 2 of 7 gives us back the input 7. And log in base 2 of 2 to the 8 gives us back the input 8. In general, log in base a of x is going to be the inverse of a to the x. In the special case where a is the number e, which is 2.71 and infinitely many other decimals, that gives log in base e of x for our logarithm, and that's going to be the inverse function of e to the x. We often call the log base e of x ln of x or ln of x. We get the same identities as before. Ln of e to the x is equal to x, and e to the ln of x is equal to x. We will use the last identity to obtain a formula for the derivative of ln of x. Once again, the graph of ln of x is obtained by reflecting across the line y equals x the graph of e to the x. In particular, the horizontal asymptote of the exponential function, which is the x-axis, translates into a vertical asymptote, now the y-axis, for the logarithm function when we're close to 0. So now finally, let's find a formula for the derivative of ln of x. If y is equal to ln of x, we want to find a formula for y prime, or in other words, for dy dx. Now, if we write each side as a power of e, then e to the y is going to be equal to e to the ln of x. But e to the ln of x, remember, that's just x according to one of our previous identity. So e to the y is going to be equal to x, and now we have an implicit equation for y. And we're going to use implicit differentiation to get an expression for y prime. So now we differentiate both sides with respect to x. Now the idea being that we want to obtain from this equation an equation that we can solve for y prime. So on the left hand side, we need to remember that y is a function of x. So e to the y is a composition of two functions, the exponential function and the function y. We need to differentiate using the chain rule version of the derivative of e to the x. So the derivative becomes e to the y times y prime. The right hand side is easier and straightforward. The derivative of x with respect to x is simply 1. So now solving for y prime gives 1 over e to the y. And finally notice that e to the y, and notice that I've use the red color each time to emphasize that e to the y is the same as x, and that's going to be replaced by x, and therefore y prime is the simple function 1 over x. So this is a new rule of differentiation that we need to remember. The derivative of ln of x is 1 over x, and its chain rule version, which we obtained by replacing x by u and putting a multiplication of du dx on the right hand side, gives that the derivative of ln of u is 1 over u times du dx. We end with a simple example of a derivative involving the ln function. Find the derivative of ln of 3x squared plus 1. This is like differentiating the ln of a function of x, call it u, where u is 3x squared plus 1. So we need to compute the derivative of ln of u, which by the formula gives 1 over u times du dx. So we get 1 over 3x squared plus 1 times the derivative of 3x squared plus 1, which is 6x. So overall we get 6x over 3x squared plus 1. Of course, we can now combine this new rule of differentiation with all the other rules, such as the product or the quotient rule, to differentiate even more complicated functions involving the natural logarithm. Thanks for watching.